I'd like to invite Don Jolly. He will be our chair for this session. If we could please all settle down and get ready for the next session. Don Jolly.
So, good afternoon, everybody. It's the last session, is it? And it's been a fantastic conference so far. This is quite an exciting session for me. I really like the large numbers that come out of these sorts of presentations, and what cables are capable of doing. So, I'm going to invite Dr. Alan Hollander to the stage to do his presentation on achieving maximum performance on SDM submarine cables. Thank you very much. Welcome.
Thank you, ladies and gentlemen. It's really exciting to be here. Thank you for I would like to thank the organization for inviting me. My name is Alan Hollander. I am a subsea architect with Infinera. And indeed, my presentation is about achieving maximum performance on SDM cable systems. So SDM cable systems are an important trend in the submarine industry. You can see from the list on the right-hand side that there are many cable systems currently being deployed or being planned, which are based on the SDM approach. Two cable systems specifically merit our attention. That's the Guyana and the To Africa cable system, which are currently being deployed. And as you probably well know, there was an interesting and successful event earlier this month, which was the landing of the Guyana cable system here in Cape Town. And these cable systems will bring an enormous amount of additional bandwidth, international bandwidth, to the African continent and the Southern African region specifically. So what is SDM? SDM stands for Spatial, some people say space, division multiplexing. And it's a concept which I would like to introduce you to. I will also point out that there are many different types of SDM a little bit later, but I will be focusing on SDM in terms of increasing the number of fiber pairs in a submarine cable system. So, SDM, it looks like, Mark, this is the older presentation. So I can continue with the older presentation, or we quickly flip to the updated one. Which do you think is the best thing to do now? My apologies, I made some small tweaks, including a few changes to make this a little bit more interesting for you. And I think something went wrong when we copied the presentation earlier today.
You renamed it to version 2, right?
Yes. Yeah, this is the version 1. So we just opened the other one.
Sorry.
No, no problem. I think it was just open.
I can't deal with Windows.
Yeah.
Okay, they open from the USB, that's why.
That one. There we go. Excellent. That will be great. So, everything done. And you can see immediately the difference and the changes I made. So, what is an SDM cable system? Spatial division multiplexing. So, to start with, a submarine cable system is simply a group of fiber pairs going from shore to shore, and optical amplifiers amplifying the light that is going through these fiber pairs. So if you would zoom into a cable system, you would see that the cable system consists of multiple fiber pairs, each with their own optical amplification. And all of these optical amplifiers require power, and the electrical power is provided through the shore ends, where there's the electrical power feed. Typical power in a submarine cable system is about 18 kilowatts, and there's a voltage differential of about 20 kilovolts. So kilowatts, 18 kilowatts, and 20 kilovolts. So that's quite substantial, and there's a limitation in how far one can go, and those limitations have currently been achieved. So if you want more amplification in your submarine system, you want to have more optical fiber pairs, or maybe you want to go a further reach, you need to do something about this limitation. One can lower the optical amplification per amplifier. One can increase distances between amplification, or one can do pump sharing, which basically means that an optical amplifier is being shared across multiple fiber pairs. And this is a technology approach that currently all the leading wet plant vendors are implementing. So what does that mean then? It means that an optical wavelength or a data carrier or a channel, there's multiple names, will receive less optical power per wavelength, which in turn will result in a lower optical signal-to-noise ratio, which is bad because basically your signal degrades. On the flip side, it will actually lower what we call nonlinear penalties. And I will explain that in the following slide. So imagine you have a wavelength and you plot the optical power per wavelength, then the performance will have a linear relationship. The performance in the submarine industry is being expressed as Q, or quality of a signal. It basically relates, it's a complex function of the bit error rate, of the prefect bit error rate, but essentially the better the performance, the better the capacity. But this linear relationship breaks down if you go to higher power per wavelength. There are so-called nonlinear propagation impairments, things like self-phase modulation, cross-phase modulation, four-wave mixing, and these are basically interactions of the wavelength with its own electrical field or the electrical field of neighboring wavelengths. And it's like a crosstalk, and it impacts performance, and they are nonlinear, which means that with higher power, they become more dominant. And as a result, if you go to higher power per wavelength, the quality will not increase as much, and at a certain moment will achieve a maximum, and progressing to even higher powers per wavelength, you actually get a decreased performance. So fiber is a nonlinear medium, and you get this effect, and there is an optimum power per wavelength, which gives you the best performance, and therefore the best capacity per wavelength, or best line rate. Can we achieve that optimum power per wavelength? We would like to, but unfortunately, if you want to achieve the optimum power for all the wavelengths in one fiber pair, for all the fiber pairs in one cable system, then you might not have sufficient electrical power to achieve that. So how is this being mitigated? The following is a theoretical example with nice numbers to make it understandable. Let's assume we have a similar graph as before, whereas on the horizontal axis we have not the power per wavelength, but we have the total optical power. And on the vertical axis we do not have the quality, but we have the capacity. Then, assuming we have a single fiber pair, and let's assume the amplifier has an 18 dBm total optical power, delivering 10 terabit of capacity, then what are your options if you would have the possibility to increase the power in your fiber pair, the optical power in your fiber pair, by a factor of 2? So you go from P to 2P, which is a 3 dB increase. Well, one option, of course, is you put all of that power in the same fiber pair, basically improving your performance, and you get more capacity, a 30% increase. With pump sharing, however, you have the ability to power another fiber pair from the same optical amplifier, and you transfer half of the power to a second fiber pair, and basically you're doubling your capacity over 2 fiber pairs. So you get 20 terabit, which is a significant increase, an overall increase. So the pump sharing actually allows you, while having a low or a lower capacity per fiber pair, an improved or increased capacity per cable system. So that's basically the power of, figuratively speaking, the power of SDM. Now, this was a theoretical example with nice numbers. Let me give you an actual real-life performance comparison. In this performance comparison, we have a regular modern submarine cable system called Maria, transatlantic between the East Coast, US, and Europe, of slightly over 6,600 kilometers. It's a modern, uncompensated cable system. It means dispersion is not compensated, large aperture, and it has 8 fiber pairs. Maria is a relatively famous submarine cable system because it's amongst, or maybe the best performing cable system in the world. Using latest transmission technologies, we were able to achieve 28 terabit of capacity on a single fiber pair with 650 gigabit line rate. This includes what we call an operational margin, so a margin that protects against the lifetime aging, performance degradations, and repair of a cable system. If we would ignore that, we would be able to achieve 30 terabit right now on that single fiber pair of that cable system. And that's very impressive. This is probably the best performing submarine cable in the world. Now, we have Dunant, which is the first SDM cable being deployed and becoming available. It has almost the same path, virtually the same distance. It uses SDM, so it has a lower power, but as a result, it has 50% more fiber pairs. With the same technology, we can achieve 25 terabit, which is a lower capacity number per fiber pair, with 500 gigabit per wavelength, which is slightly lower economics. If we take away the safety margins, we can actually deploy 26 terabit right now. So this means that the lower performance cable system actually on the same distance with probably very similar economics can achieve a lower capacity per fiber pair, but a higher overall capacity, and therefore the total cost per bit is much better, and the total capacity is much better as well. And this illustrates, although these two cable systems are strictly speaking not fully comparable because they have different technologies and vendors behind that, the distances and everything involved make this a good showcase to show the advantages of SDM. So we have SDM cable systems, and these SDM cable systems have a slightly lower power per fiber pair. So how can we still achieve maximum capacity on such a cable system, such a fiber pair? Modern transmission technologies, we're talking about 5th generation transmission technologies, have a number of functionalities that will help us to achieve that. So, for example, a modern technology is able to get to a very high baud rate, or even to change your baud rate seamlessly between different values. A modern technology has what we call long code word PCS, and a modern technology has the ability to shape its wavelengths in the spectrum space digitally to make them more spectrum efficient. I will discuss and cover the effect of ultra-high baud rates and variable baud rates in the next few slides. Allow me just to spend a little bit of time on these other functionalities. So PCS is very interesting. It stands for probabilistic constellation shaping. And it's a bit outside of the scope of this presentation to cover that, but in a nutshell, as you probably know, light is being transmitted through the fiber using a modulation concept, and these modulations, they have typically a fixed number of bits per symbol. What PCS does, it changes the probability of some symbols appearing or happening, and that requires quite a significant processing power, but basically by looking ahead in this series of bits or zeros and ones coming in, it can map these bits into symbols, and it can adjust that in such a way that some bits, some sequences of zeros and ones will appear more often, and therefore that symbol in the symbol space will happen more often. And as you can see from the top right-hand side, it gives a shape of some symbols appearing very often in the middle, and some less often. And this shape, it's a bell-curved shape. It's not exactly bell-curved, but it is theoretically the most efficient way to pack information for a given amount of optical power. And if you have the ability to look forward in your buffer, let's say the next 1,000 symbols or so, and you take all these bits into account, you can calculate a very accurate shape to give you the most efficiency. And as a result, you don't get fixed bits per symbol. You don't get 2 bits or 3 bits or 4 bits per symbol, but you can get fractional bits. So you can very fine-tune your actual bit rate of your signal. And that is a very powerful technology, very useful for example, SDM cable systems. The 3 technologies below, Nyquist subcarriers, shared wave locker, superchannels, are basically our ability to pack data channels in a spectral space as closely together as possible. So we try to make the spectral shape very square, so there is not much overlap, not much crosstalk. We minimize what we call guard bands in between, and we maximize the use of the spectrum in a cable system. And finally, Ethernet framing, that's basically a technology where if we know that we are carrying Ethernet rather than other type of client services, we can actually minimize overhead. And that means that you use less spectral space, you use less line rate overall to carry your payload, your actual service. So let me go into the effect of very high baud rates on a cable system like Equiana, for example. In this diagram, you will see horizontally and this is a simulation for an SDM cable. You see horizontally a range of baud rates, and a baud rate is basically a symbol rate. So typically that's between 60 and 100 gigabaud. That's how often the optical modulation changes. And vertically, you see a normalized reach. Actual reach, you need to think that 1 is approximately a transatlantic link. So we're talking about in the order of 6,000, 7,000 kilometers, about midway the diagram. Now, let's assume we have a 600 gigabit wavelength line rate. You will see that by increasing the baud rate, we can actually go further. We increase the reach of a channel. So how is that possible? To understand that better, you need to realize that the line rate is fixed. So if I increase the baud rate, if I increase the rate of which symbols are being transmitted, then the bits per symbol can decrease. So on the right-hand side axis, vertical axis, you see the bit per symbol, and you see that while baud rate increases, there's a similar reverse decrease of the bits per symbol. And if you multiply the two together, you will stay on a fixed line rate. And what you need to realize, of course, that if you have a low baud rate, you need to transmit a lot of bits per symbol, which means, from the picture on the right-hand side, you will have a constellation with many symbols, and these will be more sensitive to noise. Whereas if you go to a higher baud rate, you can decrease and minimize the number of bits per symbol, which basically means you do not need the same signal-to-noise ratio. You can sustain more noise. Your signal becomes more robust. So as a result, if you have a high baud rate, you can actually sustain a longer distance. If you have a lower baud rate, your reach will decrease. And if we extrapolate this, for example, we go to 500 gigabit. Obviously, with 500 gigabit, you have a lower line rate, so with a similar baud rate, you need less bits per symbol. Less bits per symbol means your signal is more robust against noise, which means that you can go further. And that's, I think, well expressed in these diagrams. Now, I would like you to pay close attention to these two dots on the right-hand side. You might ask yourself, so what is the impact of increasing the baud rate exactly? These two dots show the example of going from 96 gigabaud to 100 gigabaud. And that looks like a very small increase. But actually, just increasing from 96 to 100 gigabaud results in a 20% reach increase for this particular line rate of 600 gig. And that is, so that's basically by being able to push your technology, your transmission technology a little bit forward, you can get quite steep results. This is 5th generation technology. There will be a next generation technology. This is based on 7 nanometer ASICs, CMOS ASICs, and if we go to 5 nanometer, which will probably happen in the coming 2 years, this can probably be increased to 140 gigabaud, and when 3 nanometer becomes available, I would expect the industry to adopt close to 200 gigabaud, which is double the symbol rate that we have now. And you can extrapolate these numbers to understand what kind of performance impact that will have. So by going to a lower performing SDM cable system, but by implementing new transmission technologies, you can actually create a very good performance out of your system. The other example I quickly want to mention is the effect of being able to change your baud rate. One thing to note, and this is, I think, important for everybody who works for an organization who is leasing or buying spectrum, so not owning a fiber pair on a submarine cable system, but buying spectrum from another operator who owns the fiber pair. So what is important to note is that the performance across a spectrum is not equal. Even if you have a modern cable system with very fine balanced optical amplifiers using submerged equalizer units, you still have some physics which results in basically power or performance from high frequency wavelengths, so high energy wavelengths, going to lower frequency or lower energy wavelengths. And that's Raman amplification. And as a result, the higher frequency wavelengths need to be amplified more, which leads to higher nonlinear effects. Yeah, so that's correct. So it means that red is bad and green is good. So higher frequency, so this is terahertz, is actually losing performance, and lower frequencies are actually gaining performance. So if you are working for an organization who is about to, say, lease or buy 25% spectrum on an open cable system, keep in mind that not every 25% is equal. The 25% on the left-hand side actually has a much better performance than 25% on the right-hand side. So that is something to keep in mind. And I will show that in the following, and I will also show how the improved performance can actually be used with the right technology. So if you deploy a, let's say, a wavelength on such a cable system, on such a spectrum, I mentioned that the right-hand side is the worst performing part, so we'll start there. And if we put a wavelength there, we need to be certain that the wavelength will perform without any errors. This is what we call the FEC threshold, the forward error correction threshold. So it means that after applying forward error correction, which is built into the signal, we will have virtually no errors. Actually, we need to ensure it has a better performance because over the lifetime of a cable system, we will have things like aging of equipment and fiber. We will have potentially repairs, which will decrease the performance of the system. So to take that into account, people define a so-called commissioning limit, and your wavelength needs to comply with a minimum performance at or above the commissioning limit. Now, here's the crux. You could say that if the performance improves going from the worst part to the best part, you can just put better capacity and better line rate, higher line rate. The crux is that in our modern technologies, we have standardized client services, which are 100 gigabit based or 400 gigabit based mostly. And as such, the line rate we are using is always a multiple of 100 gig. If you have a technology which processes multiple wavelengths, like 2 wavelengths together, you could actually decrease that to a multiple of 50 gigabit, but these are step increases. So keep that in mind, that the line rate is always fixed. Now, what does that mean? It means that if you have a transmission technology with a fixed baud rate, so let's say we use 95 gigabaud, if we go from the worst part to the best part of the spectrum, in order to get to the point where we can make use of that performance, better performance in that spectrum, to go from, say, 400 to 500 gigabit, you actually need a line rate improvement of 25%, going from 400 to 500. So your bits per symbol need to increase 25%. Even if you go from 500 to 600, you need to improve by 20%. And that requires a real significant improvement of your signal-to-noise ratio. You might be able to achieve that, or you might not be able to achieve that. That's quite a requirement. If you're not able to achieve that, you basically get stuck with the same wavelength, with the same line rate across the spectrum, and on the left-hand side, you will just have more unused margin. You have a better performance, but it basically just adds some buffer. Now, the way to solve that is actually to add the functionality of being able to vary your baud rate with small steps. So what you do, rather than keeping your symbol rate or baud rate the same, what you do is, while going from the worst part to the best part of the spectrum, you slowly tune down your symbol rate or baud rate. At the same time, you slowly tune up your bits per symbol. So the line rate will remain the same. We saw that in a previous slide. But because you have a smaller symbol rate or baud rate, the channel width, the data channel width in that spectrum becomes smaller. So it occupies less spectrum, so you can put more of them into your spectrum, such as depicted here. So basically this shows that having a probabilistic oscillation shaping technology with which you can kind of tune your bits per symbol is not sufficient. You need to have a similar finely tuned variable baud rate, but if you have that, you can actually make use of that better performance. So then it really makes a difference which part of the spectrum you lease or buy. So in summary, spatial division multiplexing is an important trend. We see many new cable systems being deployed. Spatial division multiplexing is basically the ability to share optical power it's to comply or adhere to the limitation of electrical power by sharing optical power amongst multiple fiber pairs through pump sharing. As a result, optical power performance per wavelength reduces, which reduces your signal-to-noise ratio. However, in total, for the complete cable system, the advantages outweigh the disadvantages. And the benefit is that you get an overall better capacity and therefore better economics. And although you get a lower power per wavelength, new transmission technologies are available to help you to make a maximum performance out of your SDM cable system. Now, we have a very nice marketing department. They're not very salesy. They really like to understand, all that bit and byte technology, how things actually work, all the physics, and they pester our R&D people, and then they like to write this up in application briefs, trying to explain this as much as possible to the user. So if you get the PDF presentation, there's a number of papers which I would certainly recommend you to download and read if you're interested to learn more about this. This is the end of the presentation. I hope it was useful for you and interesting. Thank you very much.
So really, really fascinating stuff. And one way to excite engineers is talk those big numbers. So, but yes, I'm sure there must be some questions.
Mark.
Thanks, Mark Tinker, SAFNOG. I suppose, with a system, let's take Equiana, for example, with all these landing sites and, all manner of configuration, express, festoon, and whatnot, and all these fiber pairs. I'm guessing management and administration is going to be a big problem. I suppose we can't go the traditional way of managing, say, for example, testing between two endpoints in a DLS, a line system rather, to deliver a circuit or anything of the sort. So in an SDM world, how do you operate at that kind of scale? And I know every vendor probably has some kind of automation thing that sort of reduces months and years of testing down to hours and minutes. But then, is there an open framework that can work across multiple vendors?
Yes.
This
Yes.
sort of thing. So administration for me is obviously a big new problem with SDM, and I suppose it'll also be the same for terrestrial applications.
So there are two types of answers to your question. Very good question. One is about administration in terms of network management. New cable systems are so-called open cable systems. In the past, wet plant manufacturers would provide customers with a turnkey solution, everything, transmission, dry plant, and wet plant together, combined under a single network management umbrella. So the trend together with SDM is to have open cable systems where the wet plant manufacturer will deliver something that's completely open to any third-party transmission technology. And the reason for that is that wet plant manufacturers need to be able to compete in a very competitive environment where every few years there's a new generation of transmission technology. You need to have a large volume of sales to fund the R&D. And the reality is that manufacturers who sell into terrestrial systems, Infinera, Sienna, Nokia, have such an advantage. And the traditional wet plant vendors, NEC, ASN, Subcom, they don't. So as such, it's very difficult or impossible to compete, and that has created a difference in technology, performance, and that has in turn driven the need for open cable system and deployment of third party. Now, that means that network management systems now can be separated. You can manage wet plant separately from the dry plant, and operators are very accustomed to that. So that is like the first part of the answer. But there's a second part which is more complicated, which is about the administration in terms of performance. That has been recognized, and a group of organizations have come together in a working group, an open cable system working group under Suboptic. Infinera participated in that as well, and all the major names I just mentioned do as well. The Open Cable Working Group has come with a recommendation to use a metric called GSNR, or Generalized SNR. And Generalized SNR is basically a way, a definition actually, to measure the performance of a cable system, irrespective of what kind of transmission technology you deploy. So it's like, you know, really the performance of the wet plant, and then regardless of whatever transponder technology you use. So GSNR has been accepted as an ITU-T standard, and is now basically the de facto way to measure the performance. And that allows also operators to accept a network without transponders, a subsea network without, or even pass it on to a tenant who is leasing or buying that spectrum. So then this is a very long answer, but it's a difficult question. So with the new cable systems such as to Africa, these are high fiber pair, large quantity of landing stations. So you get like a matrix which explodes, right? It's not a point-to-point system anymore. You have like 100 different possible connections. And that indeed means that you need to be able to measure the performance of all these different links very quickly and accurately. And I think you kind of already gave the answer to it. What vendors are trying to do is to come up with an automated process using test equipment to bring up wavelengths and to quickly scan the full spectrum. You can't just do one measurement, because we've seen that performance really is frequency dependent. And the ability to scan a spectrum in, say, 30 minutes or so really helps to be able to fully review a whole complex network in a short time. Now, ideally, that type of technology is already implemented in transponders, so that if an operator selects a vendor and the technology is implemented, the vendor can do immediately a full scan of all connections without actually having to, have to import test equipment, to fly it from, place to place, to have people on site. These things can be done remotely. So that is the way how it will probably be implemented. And you can talk to your favorite vendor and ask about their abilities to do that. But that's what I see happening now. Sorry for the long answer. Any other questions?
Hi there, Saul from eNetworks. Just a practical question. We often hear about cable systems being upgraded to new wonderful super duper speeds. How is that practically done? Transponders, especially at the repeater stations under the sea. Briefly, how do the ships go and do that and keep while keeping the cable system in service?
Sorry, there's a little bit of echo. Can you maybe repeat your question?
When cable systems get upgraded to new speeds during their life cycle, how is that upgrade done? Because if the technology changes, things change, it has to be obviously be done at all the repeater sites as well under the sea. So how is that done without taking the cable system offline?
So a cable system is not taken offline. That's impossible. The cable system is always on. And the complexity of a cable system, unlike a terrestrial system, is that with terrestrial systems, you have a control loop which actually controls the optical power and gain amplification of each of the amplifiers. In an optical subsea system, that's not being done. All the optical amplifiers, submerged amplifiers, or repeaters as they're being called, they operate on a constant power, constant gain mode. this actually gives the best possible performance. So to mitigate the effects of an upgrade, where you take wavelengths and channels offline and you repeat them, there is a way where you actually replace channels with so-called dummy channels. So the way it works is that the architecture has ASE, that's amplified stimulated emission, which is basically like white light, noise, and through a wavelength selective switch, the white light or noise is slowly replacing carriers that need to be phased out. So basically what you do is like you have a balance, a weight, and it's like you see in some of these movies where somebody wants to steal a diamond and replaces that with a bag of sand. So in a similar way, in an optical cable system, they are slowly phasing out, lowering the power of wavelengths across the spectrum, and then through another channel, they're slowly adding so that the total balance remains the same. In that way, all the legacy equipment and channels taken offline, and then you can slowly reverse that process and add new capacity to it. So that's basically how it's being done, and in fact, you can do that for a small part of the spectrum, and you can that leaves the rest of the spectrum and the other working channels totally undisturbed. Yeah?
Hi, Ben Madison, Work Online. That's fascinating. I didn't know that. Why is operating on a fixed gain rather than tuning it during the insertions and removals more efficient? Your description sounds like a lot more work for very little benefit. I'm sure there's a good reason, but I don't know what it is.
So basically your question is, why is fixed gain?
Why fix the gain and keep the input power constant rather than adjust the gain to the input power at any given point of time?
So all the repeaters have a fixed optical power and gain, and I'm not from a wet plant manufacturer. Such a person could probably better indicate the benefits of such an approach. Maybe it has to do with distance. It certainly has to do with stability. What's also important is that underwater you have large temperature differences. So it's a very complex process to make certain you have a very stable fiber path. Now, when you actually enter the wet plant portal, you go through an SLT, Submarine Line Terminating Equipment Terminal. That terminal actually has a lot of flexibility to balance the powers of all the different channels. And that's also being done. So there is all the lasers coming in typically have a fixed power. They go through a wavelength selective switch, and actually the wavelength selective switch can very delicately balance the power of each wavelength. It can attenuate or it can amplify very small steps across the spectrum. So say 12.5 gigahertz or even smaller. And that's actually being done. So when wavelengths are being deployed, it's first being deployed with a kind of standard setting based on theoretical calculations. And then because theoretical calculations are based on theoretical specifications, but you need to take into account real life performance, which might be asymmetrical in two differences, which is certainly not equal across the spectrum. And then typically the engineer, the deployment engineer, uses software, automated software, which goes through, I didn't mention that in my presentation, but usually there are many different parameters, like under the hoods, where you can fine-tune the performance, like nonlinear compensation algorithms and such, indeed pre-emphasis power, and all of that is being swept automatically, and then the best settings are found. And these settings are typically, you can't really calculate them, it's not really of any use, but in practice, that can give you up to 0.5 dB of performance improvement. So it is being done.
I think what that essentially comes down to is more complexity on the dry side is still cheaper than a little bit of complexity on the wet side.
That's correct.
Right? Yeah.
Yes. That's correct. I hope we're not over time.
I think one last question and then...
And for, I think, Saul, were you asking also about opportunities to upgrade the wet side as well, like replacing amplifiers? Yeah, yeah. So I think that's the reason why I think SDM is selling, because you just have more fiber pairs in the water, because typically you will not go in and replace the amplifier.
Upgrading the wet plant is very, very complex, and a cable system can cost between $100 million and $1 billion. As far as I know, on terrestrial you have so-called C-band and L-band, and it's quite common to upgrade C-band to include L-band. In a subsea, there's actually only one submarine network in the world that has L-band. For all other, so that's also a kind of spatial division multiplexing. In terms of economics, it makes more sense to go with SDM, and actually upgrading a network after 20, 25 years, it's typically taken out of the water and it's being scrapped. Upgrading a network is almost not done. Thank you very much for your time. If you have further questions, I'm happy to meet you later at the drinks. Thank you.
Thank you very much. So I guess the question now is, how do we get some of that? And I think that's going to be answered in our next presentation.